All right, let's dive right in. We all have this idea that computers, at their core, speak a language of just zeros and ones, right? A silent world of on and off. So how on earth do we get from that incredibly simple alphabet to the complex, rich digital world we use every single day? How do we actually command a machine that only understands two things? Think about it. How do we translate a complex human thought, like add these two numbers, play this song, or show me a photo of a cat, into that silent world of binary code? You know, it's one of the great translation challenges of our time, and the solution is this incredible, multi-layered masterpiece of engineering. Because that's what this is, really. It's a translation problem. We speak in ideas, in concepts. Computers speak in pulses of electricity. So let's take a look at the ingenious bridges engineers have built over the years to connect these two completely different worlds. And to really get how these bridges work, we have to start at the very bottom. I'm talking right down at the metal, with the native language of the computer's brain, the CPU. You see, every single computer processor is built to understand one and only one language: machine language. And this isn't just a suggestion, it's hardwired into its circuits. It's basically a dictionary where every single action, adding, subtracting, saving to memory, has its own unique, unchangeable code made of zeros and ones. So what does a line of this machine code actually look like? Well, it looks like this. To us, it's complete gibberish, right? But for a specific CPU, this exact sequence means something incredibly precise. It could mean take the number 97 and place it into a tiny memory slot called AL. It's a direct, unambiguous, totally mechanical instruction. Now, can you imagine trying to write a whole app or a website like this? The source material puts it perfectly. It's like trying to talk to someone by directly controlling their brain signals. Yeah, it's super precise, but it is impossibly complicated for a human to actually use for anything beyond the most basic tasks. This raw complexity was a huge problem, a real bottleneck. So we needed to take a step away from the machine, which led to the very first layer of translation. The first real step up the ladder towards a more human-friendly way of talking to computers. And that first step was called assembly language. The big idea here was just brilliant in its simplicity. Instead of making people memorize these long, meaningless strings of binary, what if we gave each instruction a short, symbolic name? A mnemonic that we could actually read and remember. And here's that leap in action. That long binary string we saw before, it becomes this simple command: MOVAL, 97. MOV is just short for move. It does the exact same thing, but now a human can actually read it. Then a special program called an assembler takes care of translating it back into the zeros and ones the CPU needs. But let's be clear, assembly is still what we call a low-level language. And for a good reason. You are still micromanaging the CPU. You're telling it exactly how to shuffle data around between its internal storage shelves. It's powerful, for sure, but it's also really tedious, it's easy to make mistakes, and your code is completely tied to one specific type of computer chip. All that tedious, hardware-specific detail was really holding programming back. The real revolution, the thing that totally unleashed modern software as we know it, required a much, much bigger jump. This was powered by the invention of what we call high-level languages, things like Python, Java, or C++. And the single most powerful idea that unlocked all of this potential is a concept called abstraction. In the world of programming, abstraction simply means you get to focus on what you want to get done, not all the nitty-gritty details of how the computer's hardware actually does it. You just describe your goal, and you let the programming language handle all the messy, low-level, mechanical stuff for you. And this is where that power of abstraction just becomes so obvious. Look at the left. To add 5 and 10 in assembly, you need 3 separate mechanical instructions just to load the numbers and then add them. But now look at the right. In Python, you just write what you mean. Result equals 5 plus 10. That's it. The difference is just night and day. This is absolutely revolutionary because it's so much closer to how we think as humans. It frees up all this mental energy so a programmer can focus on solving big, interesting problems instead of getting stuck in the weeds of managing the hardware. The result? We can build things faster, with way fewer errors, and it's just a massive boost in productivity.
Okay, but this brings up one last really important question. If the CPU only understands that raw machine code, how does our nice, elegant Python code actually get executed? What's doing that final magical translation all the way back down the ladder?
Well, the answer comes down to two types of master translators: compilers and interpreters. Think of a compiler like a book translator. It takes your entire program all at once and translates it into a separate, highly optimized machine code file that can run super fast. An interpreter, which is what Python uses, is more like a live translator at a conference. It reads and runs your code line by line, translating as it goes. It gives you more flexibility, even if it's a little bit slower. So there you have it. That's our whole journey up the ladder of abstraction. We started way down at the bottom with the raw ones and zeros of machine language. We climbed up a rung to assembly, which gave us those readable symbolic names. Then we took that giant leap to high-level languages, which let us think more like people. And finally, we saw how translators, compilers, and interpreters are the critical link that bridges that final gap, turning our thoughts back into the only language the machine really gets. So now we see all the layers of translation that make modern computing even possible. But this leaves us with one final, really fascinating question. What is the actual journey that a single line of your code takes? I mean, when you hit the Enter key, how does that one command travel from your keyboard down through all these layers to finally make the CPU do something? That is a story for our next explainer. Thanks for joining me.